Okay, the recording is going. We're starting week 7 today, which means we have one more week basically of class time. And then the week after Memorial Day, the first week of June, that will be when the final is released. So I know we have class days scheduled for that week, but probably will not use them as instructional time. Those are going to end up, I'll be here. So if you wanted to come in for some extra help, that would be fine. And I have to have grades in by that Friday, June 4th. So everything has to be done. So if you're getting overdue assignment notices from me, you need to pay attention to that. I don't send those out until something is 2 weeks late. So we're getting to the point in the term where everybody should be done with the first 2 unit tests. The 3rd unit test will be coming out next week, and then the final will be after that. So to start off with, and for those that are in class, I handed everybody a copy of this. Last week, we started off talking about systems of equations by graphing and through elimination. So, and these are materials that are in your Google Classroom accounts, so you can go in and download them, or like I've done, open them in Google Chrome. So one of the reasons why I thought this would be a good idea to talk about to start off with, is kind of a refresher, is that as I'm seeing people do the Unit 2 test, I'm still seeing a lot of people struggling with the slope. What is the slope and what is the Y-intercept? So I need to get the lights here real quick. And if you haven't done the Unit 2 test, when you get in there, pay special attention to the beginning of it. At the very start of the test, all of the equation forms are listed. Slope-intercept, which is the one that we use most often, standard form, and point slope. So there really isn't any reason why you shouldn't be able to identify the forms of the equations on that test, but I'm still seeing people get it wrong. So pay attention to the reference material that is given to you at the beginning of the Unit 2 test, because you need it to be able to graph any of these kind of equations. And especially now with systems where we have 2 equations on the same graph, it's essential. And in every one of these, I'm going to start out with the Y-intercept. Slope-intercept equation. Everybody should know this by now. Y equals mx plus b. In those reference materials, it tells you that the slope is m and the Y-intercept is b. That's where the line crosses the y-axis. So that's really our starting point for any kind of graph. And you have to be precise with these. So my starting point here is at +3 on the y-axis for that first equation. Negative slopes go in this direction. Negative always goes that direction. Unfortunately, I can't go up 5 and left 3 because I'm off the graph. So I have to go down 5, 1, 2, 3, 4, 5, and over 3 to place my next point and connect the dots with a line. So that's the first one. Second one starts at -3. It's got a positive slope, so it's going to go this direction. Up 1, the rise is 1, the run is 3. Up 1 over 3 puts me right back on that other line. And so my solution is the point 3, -2. The other reason I wanted to bring this up is because when on that unit 2 test, when I'm seeing people that are identifying the intercepts, this is the solution for this system of equation. But if all I'm talking about are the intercepts, sometimes what I'm seeing people do, I'll do it on this other one. The intercepts here on problem number 2 are at +3 and -2. You got problems in that unit 2 test that are asking you about x-intercept and y-intercept. Some people are writing those like it's a single point. It's 2 separate points. So don't forget that. Be sure that you write them as 2 separate points. For the y, anything with a y-intercept, the first value is going to be 0. That y-intercept for that first line is 0, 3. The one for the second line is 0, -2. It's not 3, -2. It's not 0, 0. And so all I've done so far is put the intercepts on here. A slope of 4 in this first problem, or excuse me, problem number 2, this first equation is the same as 4 over 1. I can't go up 4 and to the right 1. Again, that's positive slope this way. And if you were doing these kind of problems at home, I would hope that you'd be making some of these same kind of notes to remind yourself what these graphs need to end up looking like. If you can visualize the solution before you even start, you're ahead of the game already. So slope of 4 means down 4, left 1, very steep line. That's the first equation. This next equation, the second one, has a slope of -1. Well, there's no 1 in front of that x, but we know that it's there. It's assumed. If all we have is a single variable letter, yeah. If all we have is a single variable letter with no number in front of it, then the coefficient for that is actually 1 or -1, like it is in this case. So the solution on this one looks like it's right here. -1, -1. Does anybody remember how I can check that? Well, that would show you the slope if you wanted to make the continued, up 1 over 1, up 1 over 1. It would look like stair steps. But I'm asking how I can verify that that point -1, -1 is the solution mathematically for both of those equations. Plug in the numbers, right? So first equation, y equals 4x plus 3. My x and y come from my solution point. So I'm going to replace the y with -1 and replace the x with -1, because those are the values from the point that I got when I graphed it. -4 times -1 is -4, plus 3, -1. -1 does equal -1. So pretty confident about my solution. Now the other one, this off of here. No, I don't want that. Again, my solution is -1, -1. The other equation is y equals -x minus 2. Do the same substitution. Y is -1 from the point. Here, I'm going to put a parentheses around my substitution because now I have minus minus and the keep change situation. So that makes that -1 become positive. So a +1 minus 2 leaves me with -1. Confirms my solution works for both. So all of those problems on that particular handout are going to look kind of like that. You've got two equations. You're always going to start with the y-intercept. Problem number 4 is a little different because that's a horizontal line where y equals -1. A little bit different. Questions, anybody? I would encourage you to practice on those as much as you can. So all of these on this handout are in slope-intercept form. In fact, you've got the answers on here that you can check your work against also. That's part of the reason why this handout is in the materials. It gives you the correct graphs so you can see if you've got your direction correct and your solution point correct. From the graphing, again, we're still talking about systems. That's what this whole last unit is about, systems. We'll be doing a little bit with inequalities and then systems of inequalities before this next week and a half is over. So when we got systems of equations, what are the 3 ways we can solve systems? Everybody remember, we just did one of them. No, I'm talking about the process. By graphing, 2 other solution techniques. What are the other ways that we can solve systems problems? It's right on your screen, one of them.
Yeah, that's what we do before we.
Elimination.
But we don't want him to get to work.
That's the second one.
There's some code. This athlete's great. I vouched for you guys already. We'll still be him. Just
Eliminate means to get rid of something. All right? Elimination, and for these examples, means we get rid of one of the variables. And the third style is substitution. That's what we're going to spend most of our time on today, is substitution. But we got to do some more elimination problems. So again, this is in your materials. I'm going to give out a hard copy for the folks that are in here. Now, hopefully you remember from Thursday when we were talking about elimination, introducing elimination, that slideshow that we looked at indicated that this works best if we are working with standard form equations. So now we've gone to this form of equation. AX plus BY equals C. That is called standard form. The deal with standard form is it allows us to stack these problems up like addition or subtraction problems. We can line up the terms in columns like this first one here. Our X's are all in that column. The Y terms are in the next column. And you have these totals that are out here to the right. As long as we're in standard form, we can do that. Most of the time, it will be somewhat obvious which variable you want to try to eliminate. And I think those first two problems, actually the first four problems, it should be obvious which variable we are going to eliminate. Because if you look at these just like if we were adding 6 or subtracting 6 from a positive 6, that gets to 0. That's what elimination is all about. The fact that there's a variable associated with a term doesn't change how we use the term. It doesn't change what we do with it. If you look at this first problem, the X's are going to cancel because that's negative 4X and positive 4X. Same thing in the second problem. In that X column, those cancel. What about the third problem? The Y's are going to cancel. Yep. This is what I meant about saying when I said that a lot of times it's fairly obvious what's going to cancel. And after you've done that, we just add up what's left. Go down this X column, 3X. We don't have any Y terms anymore because we canceled those. 11 and 19 equals 30. Now we have a one variable equation. And what's X equal? 10. Yep. Divide both sides by 3. This is where I talk about dividing by the coefficient of our variable. X equals 10. So now what does Y equal? You've got to remember, these equations represent lines on a graph that are going to cross somewhere. So finding X alone is not solving the problem. We need the X and the Y both because that is an ordered pair. It's a point on the graph. So let's use the second equation. 2X plus Y equals 19. Now I already know we just solved that X equals 10. So 2 times 10 plus Y equals 19. 20 plus Y equals 19. So I'm going to subtract 20. Y equals -1. So our actual solution for that particular one is the point 10, -1. That's where those two lines would cross. And it works in the other one too. If I put in the 10 for X and say 10 minus a -1, well, that's the same as 10 plus 1. That equals 11. What's X? What did we get for X? Yeah. This is a system, right? As long as we're in a system, in a group of systems problems, wherever you see X, it's referring to the same thing. Wherever you see Y, it's referring to the same thing. They could put 5 different Y's in here. As long as they're all this, they look the same, as they're all lowercase y, it means the same thing. Lowercase x's all mean the same thing. Now, if they start putting capital X's in here and some other kind of fancy lettering, might refer to something different. But for us, this is just a 2-variable system problem. We're working on the Cartesian graph, right? The XY ordered pair graph. And so part of our task is to make sure that we find both of those coordinates, because that is the one point. Remember the solutions? We can get one solution. That's what this is. It's 1 point. I didn't finish that. It's -1. That's the 1 point that solves both equations. We can have no solution, which is when they're parallel. They have the same slope. And I see a lot of people getting parallel and perpendicular incorrect too on that last test. Parallel has the same slope. That's no solution for a system problem. And then infinite solutions would be where every point is in common. It's 2 different versions of the same line written differently. Questions, anybody? So all these systems problems, you're going to have to go through some type of a process to decide which variable that you want to eliminate. Does anybody remember the 2 things that we need for elimination? Same coefficient. I didn't spell it right. Same coefficient. Opposite sign. We must have both of those in order to eliminate. Remember that coefficient is the number that modifies the variable. So if you look at problem number 5, every one of those terms has a minus sign in front of it. We don't have any that has an opposite sign. I do see that the y values have the same coefficient. They're both -9. So if I take this second row and subtract the whole thing, it changes my signs. And now I have same coefficient, opposite sign with the y terms, and I can cancel them. Over here on number 6, my y values are both positive. Well, I can do the same thing. Subtract those. Change the signs. They go from negative to positive. Now the y's cancel. Same thing here. From negative to positive or from positive to negative. That minus sign, when you subtract a whole row, it changes every sign that follows. Looks like subtraction, but it has the effect of changing all the signs. 7 would be the same way. So would 8. You get down to problem 9, 10, 11, 12. Now it's a little bit more complicated, but not much. Remember that elimination is all about manipulation. We are going to manipulate these rows any way that we need to. Anybody want to try one of these on the board? Okay, thought I'd check. So if you look at problem number 9, which one of the variables would you want to try to eliminate? Okay. So we got 1 vote to eliminate y. And so what do? They don't have the same coefficient. Signs are opposite. That's good. I thought you wanted to eliminate y. How does adding 5 help you? No.
I had it there.
Right now, the coefficient for y in this first line here is 1. It's a positive 1y. You want to eliminate the y's, then that needs to become plus 7y. Because in the other equation, you have negative 7y. So adding anything is not going to do it for you. You got to look at multiples. How do I get that 1y to become 7y? By how much? 7. That we're going to multiply that whole row by 7. Right. So then underneath that, we're going to rewrite it. Becomes 35x plus 7y equals 63. Okay. We got it. We've changed that first row. We can ignore it now. We don't have to worry about this. Because now we've got these y terms that'll cancel. I can total these up. 45x, 63 minus 18 is 45. X is going to equal 1. So once you've made that decision, you just got to run with it. The numbers got kind of high once you multiply by 7, but you got to just trust that it's going to work out in the end. We could have said we're going to eliminate the x terms instead. Then I would have used a different multiple, because then I need the x coefficients to match up.
So you divided 63 by 45?
No. Nope. 63 is positive. What are you going to do with the negative 18? We're working in this whole column here. The x column gives me this 45x.
Right.
My total column, I can't ignore that other number sitting there from the second equation. I still need to use it. So 63 minus 18 is 45.
And then you just divide by 3.
Yeah, I mean, obviously the coefficient here is 45. It's the same as my total, so it's going to have to be 1. Divide both by 45, like you said.
So x would be 1.
X is 1, then you pick one of the original equations, plug it back in. So 5 times 1 is 5 plus y equals 9. Take away 5, looks like y would be 4. Once you've got one of them solved, the other one's easy, because then you just stick it back in. Whatever your solution is, plug it back in, and it'll generate the second term, the value for the other variable.
Now, will you always multiply if you don't have a number with y or with x?
It depends on what you're trying to eliminate. Because I could have tried to eliminate the x.
Okay.
And if I had done that, then that needed to be negative 10x.
Okay.
Every choice you make is going to probably involve a different multiple. It depends on which one you're trying to eliminate.
So for instance, on number 10, if we wanted to eliminate the negative 4x, we would do what?
Column, think of the column. What does that coefficient for our other x term need to be if you're going to cancel with negative 4?
Positive 4.
Right. So
you
we
would
got to multiply that whole row by 4.
Okay.
You can't add, because remember this is negative 4 times x.
Right.
We can't add 4 to x because that doesn't cancel anything.
Okay.
We multiply though, now it's 4 times x, and it will cancel with a negative 4 times x.
And then the 9 times 4.
No, you do the
Or
4 across the way here, this whole row, the second row.
So 3 times 4 and then 6 times, negative 6 times.
Yeah, every term,
Okay.
right? If you multiply anything, any one term on the row, the whole row has to get multiplied by that same number. If I wanted to, I could have chosen the y's to eliminate also. So if we multiply that row by 4, that's going to allow the x terms to cancel, because now this becomes 4x, and just rewrite it, minus 12y equals negative 24. And then I could forget about that one for the time being. Because now the 4 and the negative 4 cancel with the x, those go away.
Okay.
Combine these, negative 3y, negative 24 and positive 9 is negative 15, so y equals 5. Didn't have to do it that way though. Because look in the y column. Remember, same coefficient, meaning the number has to be the same, and opposite sign. If I wanted to get rid of the y's, I would have multiplied by 3.
Okay.
It's just whatever you see first. It doesn't matter, because in the end result is still going to be the same. So if I rewrite that, 3x minus 9y equals negative 18. Now there's a rewritten equation that allows the y terms to cancel. Negative 4x and positive 3x leaves me with negative x. Negative 8, 18, and 9 is negative 9. Now, how do I get rid of that negative x? I got to change the sign. I can't leave it as negative x.
So you would divide by negative 1.
Negative 1 is your sign changer. Anytime you need to change the sign, you multiply or divide by negative 1.
Okay.
The thing, and this is one of the things I like about elimination, is that you have all kinds of freedom. You can choose which of those columns you want to try to work within to do your elimination. Because in this case, elimination just means cancel. We're canceling 2 terms because the numbers are the same in front of the letter and the signs are the opposite. Remember back to our original definition of a zero pair. It's the same number, one's positive, one's negative. And I'm gonna guess that there's probably some problems on here where we'd have to perhaps modify both rows. Yeah, look at problem number 17. Minus 7x minus 8y equals 9 for one equation. Minus 4x plus 9y equals negative 22. Okay, well, the y terms, the numbers aren't the same, but the signs are opposite, so that's half of what I need for y's. The x terms, I got nothing. The numbers are different, signs are the same. So if I don't have the number the same number, that's all I mean when I'm talking about the coefficient. I gotta have both of these things, opposite sign. So in order to eliminate, I have to make that happen somehow. So now I gotta start thinking in terms of multiples, lowest common multiple. Well, 7 and 4, I think the lowest common multiple is 28. 7 times 4 is 28. You think about multiples, 7 times 1, 7 times 2, 7 times 3, 7 times 4. I take the number 4, 4, 8, 12, 16, 20, 24, 28. They have no other numbers in common less than that. So this is where I'm looking for the lowest common multiple. What's the lowest common multiple between 8 and 9? See, this is where it pays to know your multiplication tables. Huh?
18.
8 doesn't go into 18.
72.
72. Right, right.
I was close. I'm just kidding. Just kidding.
If we're going to change these y terms, we got to get them both up to 72. Those numbers scare me a little bit. I don't want to have to go to 72 if I can avoid it. So this means I'm probably going to move towards eliminating x. So I'm going to have to multiply the first row by 4, the second row by 7, and one of these has got to be a negative. That one doesn't matter. So let's just say the first one is the one I choose to be a negative, because I got to get the signs to change on the x term. I rewrite both of these things. This is a big distributive property problem, and we do it twice. So 28x plus 32y equals negative 36. Do the same thing with this one. Negative 28x, 63y, negative 214, 154. Yeah. Okay, just think of what it would have been if we'd been multiplying by 9 and by 8. These numbers are already getting kind of large. Cancel here. 95y. Add down this column. 10, 4 and 5 is 9. Negative 190. Well, it's not so bad after all, because I get y equals negative 2. 95 is almost 100. 100 and 100 would be 200. That didn't come out so bad. So, knowing those multiplication tables when you have to eliminate values that where both rows have to be modified. Not sure how much of that you guys could hear at home. What I ended up doing was multiplying this first row here on number 17 by -4 and the second row by 7 because I was trying to eliminate those x terms.
So on number 23, would you just have to rewrite that problem? Because it's -14 equals -3y minus 7x.
Yeah, that was not in the right order. They need to be in standard form. That's a really good question. So ideally, we want them to be in standard form, ax plus by equals c, so we can create those columns. So now you got to start manipulating. Actually, this first one is kind of in backwards in standard form. The x and the y are on the wrong side. The other one, if I flip the whole thing around, I would have -7x minus 20y equals -14. So that's this one. The other one, I'm going to have to subtract 4 and subtract 2x to get those to flip sides. Minus 2x plus 10y equals -4. And that's from both sides. And then I also subtracted 2x from both sides. Because as soon as you cross that equal sign, you go from one side to the other, you got to use the opposite. Opposite sign is going to allow you to change sides of that equation. And that's a mess on the board now.
That's what I'm like,
Sorry. I'll be so glad when we can go back all in person. Ten y stayed where it is. That's the only one of the second equation I didn't move. Two x, not just 2. It's the whole term. And I am out of room to show it here, but if I was doing it on the whiteboard, I would have done that in 2 different steps. I got to get it to go from one side of the equal sign to the other. In order to do that, I have to use opposite signs because I'm canceling it on one side, so it shows up on the other side that I can actually use it. And then it's just a matter of, if they're both on the same side, the order doesn't matter anymore. So you just move them around if they're on the same side with their sign. That's all I did with the first one. Okay, so what I would encourage everybody to do is practice some more on more of those elimination problems. Send me a picture of something that you're working on if you're not sure, and I'll give you some feedback. So now we're going to move to substitution. Hopefully everybody can see this handout, solving systems of equations by substitution. Substitution will work best when you already know that something equals something else. And that may or may not make any sense. But again, because we're talking about a system, if we have something that says y equals something in one equation then we know that y can equal the same thing in the other equation. Because the y's refer to the same thing, the x's refer to the same thing. So if you look at this first problem, right off the bat, it says y equals 6x minus 11. Okay. Sounds good. So what do you do with that? Well, look at the other equation. I got a y value in there also. This is where you do the substitution. And this is, you'll see here in a minute why this is not my preferred way of doing things. It's important for you guys to know how to do this because in some situations, substitution works great. But in a lot of situations, it's messy. Because if I'm going to substitute this whole expression for this y, here's what I get in that second equation. Minus 2x minus 3 times where the y was is now going to be that other expression from the first equation, 6x minus 11. And that all is going to equal -7. So in some respects, it's kind of it's an alternate way to do elimination because look what I ended up with. I ended up with an equation that now only has a single variable. And what I started with was this was where the y was in the second equation. So I took this expression here because it says y equals that. So wherever else I see y, I can replace it. If it said y equals 5, any place else in a systems problem that I see y, I could replace it with 5. But in this case, it says y equals 6x minus 11. And the reason I say it's messy is because now we got this other longer looking equation that's now got distributive property. So let's see if we can add on to this. And then will let me. Minus 2x. Okay, now I got to use the minus sign with the 3 to do the distributive property. So -3 times 6x is minus 18x. -3 times -11 is positive 33 equals -7. Okay, combining like terms. Minus 20x plus 33 equals -7. Now I'm going to have to subtract 33. Right, from both sides. 33's cancel here. Those x terms got combined into that term. So my next row would be minus 20x equals -40. Okay, where did the -40 come from? Yeah. -7 and -33 together give me a larger negative, give me -40. So now you can find x. Divide both sides by -20. Again, those opposites come into play, -20. Yep. X equals 2. And then let's go back to this original one. Plug it back in here. Y equals 6 times 2 minus 11. So 12 minus 11. Y equals 1. So our solution point is 2, comma 1. And see, the other thing that you'll probably notice about this substitution problem is we had one problem, one equation that's in standard form. The other equation is in slope-intercept form. What do we say about elimination? It works best if both equations are in standard form. But if you have an equation, any of these that say y equals something, y equals this, y equals that. Oh, there's the best one here, y equals -2. Then we just plug in the number. Thank God. That's an easy one because you don't have to calculate it again for y. You're going to know what the y is because they give it to you. The problem becomes when you get down here to 7 and 9, the rest of these, if you see that y equals something, then that's what you use. Whatever that something is, that's what you use to substitute. The problem is when you get down here 7 and 8, 9, 10, okay, would you use substitution on number 7? Exactly. I would never use, and I'm not going to tell you to use substitution or elimination or graphing. You got to decide that for yourself, what you feel like is best for that situation. Because in number 7, the y's are already set up to cancel. So why not just do it? Just do the elimination, right? So you end up with -9x equals 27. Easy problem to solve at that point. And then you go do the same thing, figure out what x is, plug it back in, find y. What about number 8? Well, you've got to do something. They don't just automatically cancel because they're both negatives. Well, there's an easier way. If you're looking at the y's, then I would do the same thing. All we need is for one of them to be positive.
Multiply for negative 1.
Yep. Which is the same thing as subtracting the whole row. I'm glad you guys said multiply because it means exactly the same thing. If you don't put the 1 there, if you're not saying that's multiplication, it's still a distributive problem. You distribute the minus sign. That becomes -x. That one then becomes minus, which changes it to positive. And then the last term, distribute the minus to that one becomes negative. So whether you see it as subtraction or multiplication, it's still distributive property. In effect is multiplication, right? You're going to distribute that minus sign or multiply it, however you want to look at it. It's the same end result because now that changes this to -x plus 2y equals -11. All those signs have changed in that second one. I rewrite the first one, -7x minus 2y equals -13. Now we got the y terms set up to cancel. So -8x equals -24. And all you're trying to do is get to where you've got a one variable equation that you can actually solve. Questions, anybody? All right, now 9 and 10. Let's say for a second, maybe one of you out there really does like substitution. That would be kind of rare, but it does happen occasionally. So what if you want to do substitution? How can I take an equation from number 9 and create something I can actually use to substitute. That's not really how these working in columns works until you're ready to be, because if you're going to do that with the X's, why can't you just do that with everything? And what do you get? You haven't eliminated anything. You haven't done any substitution. You still aren't any closer to being able to solve it because you still have a 2-variable equation. So we either got to get those first 2 requirements to cancel for cancellation and elimination to occur, same coefficient, opposite sign, or we got to create a substitution. And so we need y to equal something or x to equal something. And it doesn't matter what that something is. This equation here, it's easy to do that because it's 1y, right?
Multiply -6.
Nah, I'm talking substitution here.
Oh,
I'm going to add 5x to
Oh,
both
okay.
sides. Because now I got this equation, y equals 5x minus 2. There's my something I can use to substitute into the other equation where y is. It's a pain in the rear, but it is possible. And I think was that Sama that made the suggestion?
yes.
Yeah, I would have done that. I actually would have done the same thing. I would have multiplied by -6 also.
Okay.
Because I'm going to do elimination wherever I possibly can, because this is too much trouble to go through. It's a lot of extra steps to create this expression just to be able to substitute into another equation. Look at number 10. If we're going to do a substitution on number 10, can we do another one there where we get y equal to something?
Y equal -3, positive 5x.
Yep. And I think I heard Jessica in here say, add 5x to both sides.
Okay.
That's exactly right. You're basically just manipulating the equation, solving it for y to put it in slope-intercept form. So now you've got your expression that's equal to y that you can substitute for. And that's really what substitution is in a nutshell. Where it gets harder though, okay, look at number 11. It doesn't have to be y equals something. Number 11, if we subtracted 3y from both sides here, then we would have a new equation, x equals -3y plus 1. Okay, well, now we can substitute for x. It doesn't matter which one we want to try to substitute for. If we can work it out so that y equals something and x equals something else in a different problem, that's perfectly fine. And all these are set up that way until you get down here to number 17 and 18, 19, and 20. Oh, 20 is not too bad. We could work with 20. But I guarantee you, all 3 of those other ones, I would do by elimination before I would do substitution. Because think about what you have to do. If I'm going to take this equation, this first equation in number 17, -3x minus 4y equals 2. If I'm going to create something just to be able to say, okay, now I have an expression where okay, let's solve it for y. I'll put it in slope-intercept form. If that's all I'm trying to do, I'm going to have to add 3x to both sides. And so that leaves me with negative 4y equals 3x plus 2. Now I got to divide by negative 4. Negative 4. Negative 4. Oh, this is really getting messy now, because now y equals negative 3/4 x minus 1/2. I don't want to mess with those kind of numbers. All those fractions, do substitution with that? No way. And I had to go through all that work just to come up with an expression that I could substitute into the other equation for y. This is already set up to eliminate. The x's go away right away, 3x and minus 3x. Don't make this harder on yourself. Take the easy way. So remember at the beginning, I said substitution works great in some situations. The best one was here in number 5, because it tells us what y equals. We got a number. So if I'm going to take that and substitute it into the other one, much easier. 4x minus 3, that's times 2, because that's minus 3y is multiplication, equals 18. 4x plus 6 equals 18. Take away 6. This one I would do elimination because there's not much, it doesn't really create any difficulty. So 4x equals 12. Divide both sides by 4. X equals 3. We already know what y is, so they gave us half the answer to begin with. If you already have something that's solved for y and you want to do the substitution, go for it. Otherwise, you got to convert it back into standard form. So part of your task here in this unit, honestly, is to figure out where you're going to use each kind of solution technique. Okay, so back, let's see, I think, no, not that one. I'm going to find it here just a second. Now, I didn't print out this page because it's in the materials, and I felt like today it would be better if we actually just jumped into some of the examples. But this handout that's in the materials kind of goes through the substitution stuff step by step. And this one here, this first example, says solve the system by substitution. It's exactly like the one we just did, that I just did on this other sheet, where I already knew what y equaled, and that was actually a number. Step by step. Same thing here. You've got an expression here where y equals something that you can substitute. This last example is the perfect situation, another perfect situation for substitution. Y equals 3x plus 11 and y equals negative 3x minus 7. Which one do you want to substitute? Well, we got two different things that are equal to y. So what does that tell you about those two different things? They're equal to each other. Does 50 cents equal 2 quarters? Does 50 cents equal 5 dimes? Does 5 dimes equal 2 quarters? Yes. And this is the kind of magical, if you will, substitution problem where you just make them equal to each other. Because they are. They're equal to each other. They're equal to the same thing. So they have to be equal to each other. That's why I used that little money example. Because it doesn't matter what coins make up 50 cents. They're all equal to 50 cents. So they're all equal to each other. So anytime you see different expressions that are equal to the same thing, they are automatically equal to each other. And another way to show that is I could make this a more complex equation. Looks more complex because now I stuck equal to y in the middle of it. Well, it doesn't change anything. I don't even need that there. I know they're both equal to y. So I can take that out. They're still equal to each other. So there's a couple other problems on here to practice with if you want to. But that is substitution, elimination, and graphing. Pretty much covered in all of those. And if you need to, go back and look at these slideshows again. Questions, anybody? That's going to be a good stopping point for us. So try some of those other problems on those handouts. We got another week or so to practice on these because Thursday we will do inequalities on the graphs. Now there are two variable inequalities, not just a single variable inequality. The graphing is a little different. So bring your colored pencils if you have any. I got some if you want to borrow them. So we'll get the color.
I'll bring my crayon.
Crayons are good too. Markers. Okay, thanks for being here, everybody. Okay,
Thank
see
you.
y'all Thursday.
Thank you. Bye.
Thank you.